All right, folks. So we are learning about standard deviation. Hang in there with me, guys. I promise it's not as hard as it's going to sound and seem. The more we do it, the more practice we do, you're going to be great. So, quick recap. We are talking about variability this week, right? So, variability is a measure of how different scores are from one another, right? So, we can think of this also, right, as how different scores are from one particular score, the mean, which is going to be our standard deviation. So if we think about it, right, if I have 3 data sets and right, one of them is 7, 6, 3, 3, and 1. The next one is 3, 4, 4, 5, 4. And the last one is 4, 4, 4, and 4. Those all have a mean of 4. Right. So, but that doesn't mean nothing about how different those scores are from one another. Right. So we can use the range, right, which is just how far apart the biggest score is from the smallest score. Super easy, right? Highest value minus the lowest value. Or we can look at the IQR, right, the interquartile range, which means that we are going to look at the 75th percentile minus the 25th percentile. That's going to give us the IQR, right? That tells me about the middle half of my scores, right? So sort of ignoring outliers, right? IQR is good when there are a lot of outliers, but the middle part is useful, right? The middle part is what we kind of care about. But the range and the IQR still don't really tell us much, right? We're only looking at a handful of variables or a handful of values out of this variable, right? It's only telling us about certain ones, not about all of them. So the standard deviation comes in handy here, right? And this is the average amount of variability using all the data points, right? It's the standard deviation represents the average distance from the mean, right? That's the simplest way we can think about it. So if there's our mean in the middle, right, our average, right, then there are scores, right, that are either higher than the mean or lower than the mean, and we need to figure out, right, what the average distance is from all of them to the mean. That tells us, right, how spread out the data is or how clustered it is together. So you might be saying the average what from the huh? Right, so the larger the standard deviation, that means the larger the average distance is from each data point from the mean of the distribution. Right, so it's approximately the average distance between 2 data points, right? Any 2 data points, this should be about the average distance, or the average distance between, right, one data point and the mean, right? That's what we're using, the mean. So, right, this is also another way you can think about it. They talk about this in the Crash Course Statistics video that I had you guys watch, right? The average amount you would be off if you guess the mean for a randomly drawn member of your population, right? So in that video, it was with the apples, right? And being at the fair and trying to guess whether this person is pulling out an apple or whether it's something else, right? So this is where standard deviation comes in handy. And so before we even get into the math, let's just stop and think about this for a second. So the average height of women is 64 inches, right? 5'4". Knowing what we know about humans, which of the following is a reasonable guesstimate of the standard deviation, right? The average distance someone is from the mean, which is 64 inches, 5'4". So do we think that it's 12 inches, right? That the right, average distance from 64 inches, 5'4", is a whole foot? That sounds like a lot, right? 0 inches, a half an inch, 2.5 inches. What do we think? Well, if you said 0, you're wrong. If we said 0, right, that means that every single woman would be 64 inches tall, right? No deviation, no change, no variability. Well, that's not right, right? Not all women are 64 inches tall. That doesn't really make any sense, right? So if we guess 2.5 inches, that's probably a pretty good guess, right? So in this visual representation, the standard deviation is 4, right? So this means it's a little bit still spread out, but it's probably closer, right, to what the standard deviation is for height, right? That most people are like around, right, 2.5 to 4 inches, right, different from the average of 64. Right, for example, I'm like 5'7", right? So I am, right, 3 inches taller than the mean, right? And most of us will fall within, right, 3 to 4 inches. Right, this is a pretty good guess of how close we are to the mean. So some of these characteristics, right, of standard deviation, when we have the bigger the mean is, well, it's likely that our standard deviation is going to get bigger. It's not necessarily true, but that's a pretty good guess, right? And that kind of makes sense, right? Because if you're dealing with really big numbers, right? You're like looking at 563,000 compared to 575,000. That's still a 12,000 things, right? A 12,000 whatever difference. So pretty big, right? Even though it seems like when we work with numbers that are that big, right, there's not a humongous difference. But there kind of is, right? If we look at raw numbers, right? So the bigger our means are, the bigger our standard deviations will typically be. Our standard deviations, though, are sensitive to outliers. And it is always going to be greater than or equal to 0. If you come up with a negative number, you have done something wrong. A standard deviation will never be negative, right? Because how can you be negative distance away from value, right? That doesn't really make sense. You're always going to, right? Distance is always a positive measurement. You can't be negative distance, right? Even if I dug down into the ground, right, I wouldn't be, right, negative 3 feet away from my computer. I would still be 3 feet away from my computer, right? Just 3 feet down instead of 3 feet up, right? So you always are going to have a positive number when you calculate your standard deviation. So one of the really cool things about standard deviation, this is going to start helping us get into inferential statistics, right? Trying to figure out if something is statistically significant. So in a normal or symmetrical distribution, which is what we're going to be operating under the assumption of for this class, because we don't need to worry about asymmetrical or abnormal distributions. And that is not intro level stuff. So we're going to assume that our distributions are normal. And so in a normal symmetrical distribution, right, this is what we call a bell curve, right? So let me draw you a bell curve real fast if you don't remember what it is from the crash course video or from our previous conversations about distributions, right? A bell curve, right? Something like this, right? That is our bell curve. So with the 68, 95, 99.5 rule, which is a really cool rule, in a normal or symmetrical distribution, 68% of all cases will be within 1 standard deviation of the mean, right? So if I have my bell curve and I have, right, my mean here in the middle, somewhere that way, then I'm going to flip my video. That's going to make this easier. Right, so then 1 standard deviation, boop, 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 boop. Right, SD1, right? About 68% of everything is going to be, of all cases, are going to fall within 1 standard deviation of the mean, right? So if I add the standard deviation to the mean, right, on one side and subtract it from the other side, that's going to leave me with 68% of cases are going to be in between those two, right? So then next up, we have the second standard deviation, right? If we add standard deviation to the mean twice and subtract it from the mean twice, all right, then that tells me, all right, I just added some space here on my belled graph, and that tells me that 95% of cases will be within 2 standard deviations of the mean, right? So that now tells me that anything that is more, right, that I have 95% chance that any one thing I pull out of the data set is going to, I have a 95% chance that whatever it is going to be within 2 standard deviations of the mean, which means that if it's not within 2 standard deviations of the mean, that's only a 5% chance. Like that starts to tell me that there's something weird about this one, right? And then, right, 3 standard deviations away from the mean, that is going to encompass 99.5 of all of my cases, right? So that means 0.5 cases on this side and 0.5 cases on this side are not going to be, 0.25 cases, percent of cases are going to be on this side of the mean, of the mean. 0.25 cases on this side of the mean are going to fall outside of 3 standard deviations. If I get anything that is outside 3 standard deviations from the mean, that's an outlier, right? And that is something that is going to be weird, right? We expect almost everything in a normal distribution to fall within 3 standard deviations of the mean. So let's calculate the mean. Well, first of all, let's play another guessing game. Right now that we know this about the our standard deviation and this 68, 95, 99.5 rule, if I tell you that the average home price in Greensboro is 225,000, right? That's the average home price for a home in Greensboro. What is the likely value of standard deviation? Is it 500? Right, if we add 500 plus 500 plus 500, that's $1,500. Does that tell us that 99.5% of all houses in Greensboro are going to be $225,000 plus or minus $1,500? That doesn't sound right. What about 5,000? So 5,000 plus 5,000 plus 5,000, that's 15,000. 15,000 plus or minus, of 225,000, that's still a pretty small number, right? That's no way that's going to encompass, right, 99.5% of all houses in Greensboro. But if we look at 500,000 times 3, that's 1.5 million. That's way too much, right? That we went way overboard there. So it tells us, right, 50,000 is probably a pretty good guess, right? 150,000 plus or minus, right, 225,000 plus or minus $150,000. That's probably going to be where most homes in Greensboro fall as far as value, right? There are outliers, but that's probably a good guess, right? At least better than the one above it and the one below it. So standard deviation, right? Before we even get to the math, right? Think about it in terms of what makes sense, right? Does it make sense that, right, if I multiply my standard deviation by 3 and I add that from the mean and subtract that from the mean, does that encompass the vast majority of the data? If the answer is no, then we've probably done something wrong, right? So let's calculate it. If you do not already have a piece of paper and a pencil and you are not currently taking notes, I would highly suggest you do that right now, because we're going to walk through how to do this step by step. And if you are not taking notes, you should be, right? Because you're going to need to know how to do this. And so as we walk through step by step, I'm going to show you how to do it. I'm going to show you how to do it like this, this one way, and then I'm going to show you how I actually do it when I am calculating it for real by hand. You can also use Excel to do this if you are handy with Excel and know all the tips and tricks. But I figured why add one more program to confuse you. So I'm not going to teach you how to do it through Excel, but if you are handy with Excel and use the formulas and stuff on a regular basis, you can do what I do by hand on Excel. But we'll get there. So remember, the standard deviation is approximately the average distance from the mean. So first, we have to calculate the mean, right? How do you calculate a mean? Right, you add everything up and you divide it by the total number of cases. So how would you calculate the mean distance from the mean? Right, in theory, you would think, right, you would look at all of the, you look at the mean, right, and look at all the data points, figure out how far away those data points are from the mean, then add those up, divide it by the number of cases, ta-da. You're close, but not quite. So let's start with finding the mean. So I give you these numbers, right? This is our data set. So our sample is 96, 76, 88, 86, 98, 80, and 78. If it helps you think about these as, right, not just numbers, but representing something, we can think of this as an exam score, right? I've taken a sample of my class, and I took 7 random people out of the class, and right, these could be exam scores. So if that helps you think about them that way, let's talk about it that way. So I have 7 exam scores, right? 96, 76, 88, 86, 98, 80, 78. 7, right? My N is 7. If I add all those up, remember that's what that sigma sign means. Add all those up, that gives me 602. I divide 602 by N, right, by 7, and that gives me 86. So the average score of all of these students was 86. Okay, so, all right, cool, got that. Step 1, done, found the mean, 86. Then we're going to find the distance from the mean for each case by subtracting the mean. right? So we're going to take all of those cases, we're going to write them out in order, and we're going to see, right, 96 minus 86 is 10. 76 minus 86 is negative 10. 88 minus 86 is 2. 86 minus 86 is 0. 98 minus 86 is 12. 80 minus 86 is negative 6. 78 minus 86 is negative 8, right? So what we've done in terms of formulas, right? So we're also going to build the formula as we go. Right, to find the deviation from the mean, right, the difference from the mean, we have to take our each case and subtract the mean from it, right? That makes sense. How far away are you from the mean, right? So next step, we are going to add all those up, right? Because that's what we would do to find the mean, right? To find the average is we take all the things, we add them up, and we divide by the total number. But unfortunately, we can't do this because you will notice, right, when I take all of these deviations right here, all right, and I carry them over to the next slide, right, then 10, negative 10, 0, 2, 12, negative 6, negative 8, I add all those up, I'm going to get 0, right? The sum of differences from the average will always equal 0. This is a really good way to check yourself and to make sure you've done the step correctly. I always do this when I calculate it by hand because we're going to have to do this math anyways, and we might as well double check ourselves and make sure, right? It's one quick step. We might as well double check and make sure that we've done this correctly. Remember, when we're doing them by hand, I'm never going to give you a ginormous number of things to do this with, right? I'm never going to give you 500 variable points to calculate the standard deviation by hand. Never in a million years, right? I would never do that to you. I promise you. And we're always going to be operating right within somewhere around 10 cases when we do this by hand. So this really doesn't take a whole lot of time just to check ourselves, right? And make sure that we have added these up correctly or subtracted them correctly. So, right, we have our differences. So that, again, we're building our formula as we go. So we've taken each case, subtracted the mean from it, and added those up, right? We get 0. So that doesn't really work for us. So what we have to do is we have to square the numbers, right? Because what happens is they end up canceling each other out, right? When we look over here, right, this negative 6, negative 8, negative 10, those all add up, right? And then we look at 10 and 12, 10 and 2 and 12, right? Those all add up to 24. The other ones add up to negative 24. Like, oh no, right? They've canceled each other out. So how do we avoid having them cancel each other out? Remember what I said, that distance can't be negative, right? It doesn't really make sense to think of distance as negative, right? So we have to make them positive. And using the absolute value symbols don't really work. It's weird and confusing algebraically. So what we do is we square them, right? Because if we square the differences, then that makes all of them positive, right? Because a positive times a positive is a positive. A negative times a negative is a negative, and then a negative times a positive is a negative. But, right, if we square it, then we are multiplying these two things that are like each other, right? Either two positives or two negatives, and that's always going to give us a positive number, right? So remember, hopefully you're writing this down as we go and working out this math with me, so you remember where these numbers came from, right? So these are the differences: 10, negative 10, 0, 2, 12, negative 6, negative 8. I'm going to square all those, right? So 10 times 10, negative 10 times negative 10, 0 times 0, 2 times 2, 12 times 12, negative 6 times negative 6, and negative 8 times negative 8, right? When we square them all, it makes them all positive, right? So now I have 100, 100, 0, 4, 144, 36, 64, right? Now I'm going to add all these up, and I should not get 0 this time, right? So now I have 100 plus 100 plus 0 plus 4 plus 144 plus 36 plus 64, and that gives me 448. Right? So remember, right, we are building the formula as we go. So we had this before, right? X minus X bar squared. Now we sum those, right? So the sum of all cases minus the mean squared. Cool. So now we are going to divide by the n or n minus 1, right? So what does that mean? So we have sample statistics and population parameters. Unless it is explicitly stated to you that we are looking at the population, we are almost always going to be operating with a sample statistic, right? So think back to this, right? We've talked about this before. I'm sure you've heard this in your other classes before. A population is when we sample every single possible, right? We survey every single possible person. But if we can't talk to every single possible person, right, then it's a sample. So chances are we are almost never going to be working with the population, right? Because the population means every single person, right? So for our GSS data, right, our general social survey data, it is surveying Americans, right? But they don't ask every single American, right? Have you ever been surveyed for the general social survey? No, I'm going to guess you have not, right? So we're not looking at the entire population of all US people, right? We're looking at a sample of them. And so in that case, we're using a sample statistic as opposed to a population parameter. If we're talking about a population, right, then we can make more statements, right? We can say it's not a statistic, it's a parameter, because we know everything there is to know, right? We know every single data point. But because we don't know every single data point, most of the time, we operate with sample statistics. And when we're doing a standard deviation for a sample, we tend to underestimate the true population standard deviation, which is why we subtract 1 from n, right? This sort of accounts for that underestimation. We're going to come back to this after we're done calculating the standard deviation, and we'll see how looking at the n or n minus 1 changes depending on how that changes, right, our standard deviation. But it's going to be helpful that we know how to calculate standard deviation before I start talking to you about yn versus n minus 1. So for right now, just remember, if you have a population, right, population standard deviation, right, it's going to be marked with this lowercase sigma, right, which is like the circle with the little boop through it, kind of like a cursive O without the little loop-de-loop. So, right, that's our sigma, lowercase sigma, and we're going to divide by n. But because we're almost never going to be working with the population, we are going to do the sample standard deviation, which is marked by a lowercase s. And then for that case, we are going to divide by n minus 1. N minus 1, sometimes you'll also be referred to as the degree of freedom. Right, the answer to that will be your degrees of freedom. That's going to come in handy later. So keep that in the back of your head. Right, the n minus 1 is degree of freedom, but we're not going to talk about it that way for standard deviation. But when you hear that word again, I'm going to ask you, what is a degree of freedom? And you should be able to tell me n minus 1. Okay. School. Cool. All right, so we are going to take our formula, right? We have our sum of x, all cases of x, minus the mean squared, sum all that up. Then we're going to divide that by n minus 1, right? Because this is a sample of the class grades, right? So my n is 7, so I do n minus 1 is 6. So then, right, I carry over my information from the last time we were doing stuff, 448, divide that by 6, that gives me 64, right? Congratulations, you have found the variance. So, right, when we've done this, right, remember when we squared all of those distances and values from the mean? That means that our answer is now in a squared unit of measurement, right? So we did this stuff with it, right, to be able to find the standard deviation, but we've got to then go back and sort of fix that, right? So that the mean, which is not a squared unit, right, that our standard deviation is in the same level of measurement, unit of measurement, right, as our mean. So right now our variance is squared, right? And variance compared to mean doesn't make a whole lot of sense because you're comparing one thing that's squared to something that's not squared. So to find the calculation for the standard deviation, we have to take the square root of the variance, right? So we are sort of going backwards and sort of accounting for that squared thing that we did to be able to calculate it. So we're going to play with the numbers to be able to calculate it, and then we have to put them back the way we found them, right, to be able to compare the two, right? So to find the standard deviation, we take the square root of the variance. So the square root of the variance is the standard deviation. So for a sample, right, we have the square root, right, over here, right? So remember our order of operations, right? We are going to do what is inside parentheses first, right? So we do that. We do our exponents, we add all things up, right? Very, very, very last thing we do is take the square root. So, right, our variance is 64. So we take the square root of that, and the answer is 8, right? So our standard deviation for that is 8, right? So if we go back to our original data set, right, looking at these, the average, right, the average score is 86, right? So 86 is the average, and our standard deviation is 8, right? So if I add 8 to 86, right, that tells me that, right, 92, right? That's 92. So nope, that's not right. That's not 92. That's 94 because math is hard, right? So 94. So that tells me, right, that 68% of students, right, either got somewhere between, right, 94, and then I subtract 8 from 86. That gives me 78. I know that part's right. So that tells me, right, that, right, 66% of students, 68% of students, right, are going to score somewhere between 78 and 94, right? And look, that totally makes sense because we do have folks who have gotten lower than a 78, and we, do have folks that have scored higher than a 94. So the next thing, right, if I add, right, 8 to the next one and subtract 8 from the other one, right, so that now gives me over 100, so 100% plus. And then I subtract 8 from the 78%. That's going to be 2 standard deviations away from the mean of 86. Right, so that tells me now that 95% of all students, in all likelihood, right, 95% of all students scored somewhere between a 70 and 100. And that looks about right. Right, so that is accounting, right, for the idea that maybe there are some students who scored a little bit lower, right? Maybe there are folks who did extra credit or used a token, right, who might be higher than 100. But 99.5% or 95% of all students are falling between 70 and 100%. And that sounds about right to us, right? Right. So let's keep going forward. Right, so here are the steps to calculate standard deviation. First, you're going to find the mean. Then you're going to subtract the mean from each case. Again, I will always suggest that you sum the differences to make sure that your answer is 0. Then you're going to square the differences, sum the squares, divide by n or n minus 1, and then find the square root of that previous step. So, like I told you, I am going to walk you through this. All right, so this is the way that I do it. Okay, fine. I'll erase all my answers so that we can do this together. So the way that I do this, almost always, where'd my dry erase marker go? Hold on, let me pause and adjust myself momentarily. How do I pause? What is happening? Okay, I think I've got it situated. So, all right, I have a data set here, right? 5, 8, 5, 4, 6, 7, 8, 8, 3, 6. All right, so what I'm going to do, right, first things first, always want to find the mean, right? So I'm going to add all these up together, 5 plus 8 plus 5 plus 4 plus 6 plus 7 plus 8 plus 8 plus 3 plus 6, right? My n is going to be, right, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so my n is 10. And my mean is going to be, can you tell me? Can you tell me? Okay, the answer is 6. Okay, all right, so add all these up together, right? That gives me, divide it by 10, that gives me the mean of 6. So the next thing that I'm going to do, this is how I always do it, right? I am going to make myself a chart. Right, just ignore all of the chairs that I had to go through to figure out how to prop up my whiteboard to the point where y'all could see it. All right, so what I'm going to do is I'm going to write X in my first column, right, and make myself a chart. You'll see it in just a second. Right, and now what I'm going to do is I'm going to write all of the values of X, possible values of X, in order, right, descending from the top. So I have 8, all right, and then I have another 8, and then I have another 8, and then I have a 7. Ignore all my weird noises. And I have a 6. 6. And then we have 5. 5. 4. And 3. Right, so that's what I've done. Right, I have written out every value of X into a chart form just like this. Right? Okay. So the next thing I'm going to do, right, because I've already found the mean, is now I'm just going to have X bar. Oh, okay. My computer's just doing stuff. All right, so X bar, all I'm going to do here is just write the mean. right? So it's going to be the same every time. 6, 6, 6, 6, 6, 6, 6. That's kind of creepy, right? Just like that. Boop, boop. Super, super duper simple, right? Next step, right, that we do to find the standard deviation is just to do x minus x bar, right? To subtract it to find the mean, right? Subtract the mean from each value, right? And so now since I have them side by side like this, right, then it makes it super easy to do that 8 minus 6, 8 minus 6, and so on and so forth, right? So 2, 2, 2, 1, 0, 0. 5 minus 6 is negative 1. 5 minus 6 is negative 1. 4 minus 6 is negative 2. 3 minus 6 is negative 3. Right? Just like that. Boop, 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 boop. Okay. So then, right, I need to square those. Right? But before I do that, right, I am going to double check myself just to be careful. Right? So I know my zeros are going to be 0. Right? Those cancel each other out. Negative 1, right? Negative 1 cancels out that positive 1. Negative 2 cancels out that positive 2. Right? Negative 1 plus negative 3 is negative 4. 2 plus 2 is 4. All right, cool. When I add all those up, right, I made myself a new little box right down here. I'm going to call that sum. All right, I'm going to call these sum right there. All right, add all those up. I get 0. That means I have done something correct, right? I am on the right track. So the next thing I'm going to do is just write x squared up at the top like that. And what am I going to do? I'm going to square all these. Right, so then, right, 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4, 1 times 1 is 1, 0 times 0 is 0, negative 1 times negative 1 is 1, negative 2 times negative 2 is 4, and negative 3 times negative 3 is 9. Right, so now I have, boop, boop, all of my square values. And now, look over down here. I got my handy little sum box down here. So now, these are all in order, super easy for me to do, to just add all them up. Right, I'm going to add them all up. Right, that gives me 28 total. Right, awesome. So now I have, right, this value that I need. So the next step that I am going to do is divide it by n minus 1, right? Because like I told you, if I don't specify, if nobody tells you what to do, always assume it's a sample. So I'm going to take 28, right? I'm going to divide that by 10 minus 1, which is 9, right? Which gives me 3.11. Don't worry, I didn't do that in my head. I already had the answers written down, right? So that gives me 3.11. Remember, that's the variance, right? That's the squared value. So I have to take the square root, right, to return it back to its natural state. Right, so if I take the square root, I've run out of space. Ha ha ha. Right, so 3.11 equals, right, 28 divided by 9 equals 3.11. So then what I'm going to do, right, to find the actual standard deviation is take the square root of 3.11. All right, again, I already have the answers written down. I am not doing this in my head. I am not that smart. Right, so the square root of 3.11 is 1.76 after rounding, right? So my standard deviation for that set of scores, right, is 1.76. Right, so I'm going to come back up here, boop, and I'm just going to add that boop, to my little information about my data set. And I just put my finger in the 6. There we go. All right, and now look at all this information I already know now about my data set. I can tell you the range, right? Range is going to be 5. That's 8 minus 3. All right, and look, I already know so much about this data set now. I know how many things are included in it. I know what the average is. I know what the standard deviation is, right? How far apart on average all of these numbers are going to be from the mean, right? I'm going to know my range, and I know a lot about this data set now. Right, I've learned a lot about the variability, right? How different these scores are from one another, right? It's a pretty low standard deviation, right? 1.76, kind of small. So what does that tell us? There's not a lot of variability. And you know what? That's right. There's not a lot of variability, right? That range also confirms that for us. Pretty small set of numbers, small standard deviation, not a lot of difference from the mean of 6.